So we're going to be looking at how to use Desmos or graphing calculator to model trig functions. So things that are naturally occurring in a wave where we're going from a high to a low point. I've included in this video screenshots from Desmos. I still prefer to use a TI-84 for sine regression. I just typically have an easier time with that. But I know that at home you all may not have access to that calculator. So I did use Desmos, even though I didn't think it was quite as easy to do. And I've linked that in on the page for this week's module under supplemental materials. So for this first problem, the table below lists the average temperature of Lake Erie as measured in Cleveland, Ohio on the first of the month for each month during the years 1971 to 2000. So for example, T equals 3 represents the average of the temperatures recorded for every March 1st through the years 1971 through 2000. So each data point is an average of the temperature that occurred on that date for those years. So the first thing that we're going to do is plot the scatter plot to see the pattern of points, and then we're going to fit a line to those points. So I went to Desmos and plotted a table to create the scatter plot, and then visually this is what I see on Desmos. So I can see that if I follow the curve, what I'm seeing happen here is that I would have a sinusoidal graph, meaning that it's a wave-like pattern. So once we can identify that we have a wave-like pattern, we need to fit the equation. So you can use the regression function on Desmos. The y sub 1 is equal to sine of, and then I put in b x minus 1, all of that. Now when I did that, I got this really ugly black box, and I couldn't see the points because I think Desmos was just struggling with the b value. So what I did is I used the regression function that has the sliders, and so then I could adjust all of those values. So I just kind of played with this until I got a graph that looked close. I also did use the A, B, C, D values that I got when I used the other regression. So the equation for this would be 21 sine of 0.5 x minus 56 plus 54. And again, the idea of a regression is that it's an approximate or a close fit, but not necessarily, like I don't have to hit every single point, which you see happening on this graph. So the next question asked us to use that model to predict the average temperature at Lake Erie on April 15th and September 15th. So if you remember from the problem, they took and recorded on the first of every month, which means I want the 15th, which is approximately half. So I just went into Desmos and asked Desmos to graph at 4.5, x equals 4.5, and x equals 9.5. And then I was able to find those intersection points to give me an approximate temperature, because again, the graph, the output is the temperature. So according to the model, the average temperature on April 5th would be about 42 degrees Fahrenheit, and the average temperature on September 15th would be approximately 74 degrees if we rounded our answer to the nearest hundredth. So again, for time purposes on the video, I didn't show you having to go in and play with those values on the plot. It did take me a little bit of time to kind of get that and figure that out and move those around. So if you need help with that, if you'll please come to the, make sure that you come to the live class times, or ask me to set up a time with you for some office hours to help you play with the features on Desmos if you need help with that. But that's how I would use that graph to answer those questions. So I did the same thing for the next part, although for this one I had to graph two separate because they're asking for Honolulu and Miami, and then we're going to make some comparisons between the two. So I took the data for Honolulu to fit those to the points. And so here's my approximation for Honolulu. So again, it's not a great fit, but unless I got really specific with some decimal answers, you know, we could sit and play with that all day. If you have a graphing calculator, TI-84 or TI-83 at home, this would probably go much faster, because I feel like in class when I do this with those graphing calculators, I can get much better answers and much more precise answers. So here's Honolulu's graph, amplitude of 4, the K value 0.5, D, which in this case is your phase shift, is 5, and C, which is the midline here, is 85. Okay, versus Miami. So Miami, its amplitude is 7.5, which means that there's more variance in the temperatures in Miami. So we can look at amplitude to answer questions about difference change, like how much the difference is from the lowest temperature to the highest temperature in the year. We can also look at the midline. So the average temperature in Miami would be 82 if we're looking at the midline, whereas in Honolulu, our midline was at 85. So that just tells me that the average temperature in Honolulu is a little bit higher than it is in Miami. If we go back here to these questions that they're asking, so we had our models to estimate average temperature. And again, your average temperature is going to be in the at the midline. The period of each model should be 12. So if you go back and calculate that, again, because we should see the same repetition in 12 months for temperature once we repeat January to January. Variability, you're going to look at variability in your amplitude, right? So distance from minimum to maximum value would be how you would answer question number 7. And then number 8 is going to be kind of up to you. They're fairly close, but you would want to look at average temperature in, March to April. Do you want to go where it's a little bit warmer? Is that going to happen in Honolulu? Is that going to happen in Hawaii? In Miami? As you think about answering that question. So that would be a place in class. We would have had a little bit of discussion about that. And maybe once you look at that, we can talk about that during our class session on Wednesday. So the other type of application question that you will see most often used in trigonometry for periodic motion, right? So repeated height off the ground comes from a Ferris wheel, because when I get on the Ferris wheel, I'm going to load down here at the bottom bucket, right? So there would be where I'm going to load the ride. So I would start at the lowest point, and as I ride around that circle, my height off the ground is going to be this consistent wave, okay? And so this right here would be time is equal to 0. So these graphs still have amplitude. So for a Ferris wheel problem, your amplitude is going to be half of the diameter of the circle or the Ferris wheel. Okay, because that's how far off the ground I would be. And then the period is going to be whatever the time is taking me to make one rotation on this ride. So whether that's in seconds, because it's a really small one that you might find at like a carnival or a fair, or it's one of the really huge ones like you would see at the beach or in Vegas, where you go really slowly because it's more of a sightseeing than like a thrill ride, I guess. And then your midline is going to be equal to the radius of the circle or the Ferris wheel plus the height of the loading platform. So if I'm loading at 3 feet off of the ground, and this Ferris wheel is 20 meters tall, that means that at peak height, I'm going to be at 23 feet, and the lowest is going to be at 3 feet, which gives me the total distance between those as 20 feet. And so my amplitude in that case would be 10. It's going to be half of the diameter of the Ferris wheel. And so then your midline is going to be, in this case, at 13, because that would be half of the diameter, which is the radius, which is 10, and then the loading platform is 3 feet off of the ground. So just things to think about as you're working through those types of problems. So some important definitions. So if we're going to write an equation for the Ferris wheel, describe below where time is measured in seconds. The very top of a Ferris wheel is 41 feet off of the ground. So we can even start by kind of sketching a Ferris wheel. So there's not a great circle, but there's a circle. And so the very top is at 41 feet. He's getting on at a platform that is 5 feet tall. Write an equation that describes his height above the ground while on the ride if we know the wheel makes 2 full revolutions in 1 minute, which means that 1 rotation is occurring in half of a minute, okay, or 30 seconds. So 41 minus 5 is 36. So if we think about what's happening here, he's going to get on the Ferris wheel at 5 feet, and he's going to keep making that rotation. So we're going 5 to 41, which means that our amplitude is 18 because it's half of the height of the Ferris wheel. The midline is going to be at 18 plus 5, so the midline in this case is going to be at 23. So if we start thinking about writing the equation for this, I'm going to do this even without having to use the function on the calculator. This is going to be a cosine graph. He's loading at the lowest point, so it's been reflected. The amplitude is 18. We're going to write this as a cosine graph. So the b value is going to be 2 pi over b is equal to 1/2, because it's taking him half of a minute, if we're going to let our units be in 1 minute. So if we solve this for b, I'll write this over here on the left side of my screen, 2 pi divided by 1/2 is equal to 4 pi. So we see 4 pi waves, basically. So I plug that in for b, so 4 pi. We can use x or theta, it doesn't matter. There's no phase shift because he's loading at the lowest point, so I don't have to worry about moving it to the left or to the right. And then the midline is going to be at 23, so I need to shift that up 23 units. So that would be my function rule that would model that Ferris wheel ride. So again, it goes back to what we talked about on our last video, making sure that you can find and kind of identify those things and being able to look at sine or cosine. If you're using a graphing calculator, those are always going to be done as sine functions, and then they're going to put in the appropriate phase shift to make sure that it models correctly.